Alright, so this problem we have two links, AB and CD, which are made of steel. They have a uniform rectangular cross-section of 1/4 inch by 1 inch. Knowing that they support the rigid member BCE, we are asked to determine the largest load that can be suspended from point E if the deflection at point E is not to exceed 0.019 inches. So basically on this problem I'm going to go ahead and start off by drawing a free body diagram. I'm going to have the X and Y standard coordinate system here, and I'm just going to draw BCE on this free body diagram. And so basically we're applying a load at point E, and that's here on this right side, so I'm going to call that load P. And when we apply that load, if you look at the diagram here and think about this logically, you're going to have some reactions by these two members that keep this thing in line. So you're going to have a force going upwards at point C, and I'm going to call this FCD because it's going through that link. And then on the left side here you have the link BA, and you're also going to have a force there keeping this BCE in line as it is shown here, and I'm going to call this FAB. And so now that we have what this free body diagram looks like, we actually need to find these two forces in terms of P, because we're basically going to be solving for P, which is the largest load that can be applied. So if we take the moment at each of these points, point B and C, then we can actually find what each of these forces are in terms of P. So I'm going to go ahead and start off by taking the moment at point C first. So I'm going to do my sum of moments at point C. It's going to be equal to 0. And then this is in inches. So we have here 10 times FAB. And that's coming from the problem statement, the picture up there. And then we have a negative moment for point P. That's a distance of 15 inches times P. And so solving this, we get the FAB is equal to 1.5 times P. And similarly, we're going to do the same thing for the other force as well. We're going to take the sum of moments at point B to do that force. And this equation is going to look similar, so we're going to have distance of 10, and then our force is FCD for that first one. It's a positive moment, and then we have a negative moment for point E for force P. So we have negative, it's a distance of 25 times P. And then solving this, we get that FCD is equal to 2.5 times P. So now we have both of these forces in terms of P. We actually want to go now and figure out when you apply a force P at point E, what does the deformation look like in these two links? So I'm going to go ahead and start off by solving for this deformation at point B. So delta B. And the formula that we're going to be using for that is going to be FAB times the length of AB over E for AB, which is given, and the cross-sectional area of AB, which is also given. So I'm going to go ahead and just start plugging in the stuff that we know here. So FAB, we just found that. That's 1.5 times P. LAB is 8 inches. E for AB looks like it's 29 times 10 to the 6th PSI. And PSI, of course, is pounds over square inches. So I'm going to put that in now. 29 times 10 to the 6th. I'm going to just write it out so we can cancel everything. And then they actually give us the cross-sectional area. So it's 1/4 inch times 1, and then that'll be inches squared there. So if we actually go ahead and solve for this, we're going to get that we have a deformation of 1.65517 times 10 to the negative 6th times P. So we're solving for that in terms of P, just like we did with the forces. Now for the deformation at point C, we're going to do the similar thing here. Same thing pretty much. This one we're just going to be doing the force in CD, everything with CD. So FCD, LCD over ECD, ACD. And we're going to plug in all the stuff that we know. So we have 2.5 times P. We have 8-inch length. E is the same, 29 times 10 to the 6th pounds over inches squared. And then the cross-sectional area is also the same. So solving for this, we're going to get 2.7586 times 10 to the negative 6th times P. So now we have two deformations in terms of P. And what we're going to do now is we're going to go ahead and draw a deformation diagram and show what this thing looks like as a force is applied at P. So this here, this horizontal line, is the original position of BCE. As we apply a force here on the right side, it's basically going to deform in this sort of shape. Obviously this is exaggerated, you're only going to get a very small deformation, but this is kind of what it looks like. And we can actually draw what each of these distances here are. So this here is the deformation at E. This here is the deformation at C. We have an angle theta there that is currently unknown. And then here on the left we have the deformation of B. So you can kind of think about this logically when you're making one of these diagrams. When you apply a force at point E, point C, you're going to have that go down, and then point B, you're going to have that go up, or try to go up, deform upwards. And so basically now what we're going to do is we're going to try to find this angle theta here. And the reason for that is what we're looking for is the deformation at point E. So that's what we're trying to find. And that's right here. And so we can actually find that by using the deformation at point C. If I draw a little triangle like this, we can see that the deformation at point E is just equal to the deformation at point C plus this little extra distance here, which I'm going to call delta prime. So our deformation at E is just the deformation at C plus delta prime. And basically what we need to do is we need to find what that value of delta prime is. And so these are similar triangles, so we know that the angle on this little small triangle is also theta. And then of course we know the distance here, which is 15 inches. And basically there's a property that we're going to make use of here. It's called the small angle approximation theorem. And so since these deformations are very, very small, there's this theorem that we can use, which basically states that the tangent of a small angle theta is just approximately equal to that angle theta. And so that angle theta, of course, when you have these two things equal, theta being equal to tangent theta, of course, is the opposite side over the adjacent side of that triangle with respect to theta. And so what we can do is we can plug in the opposite side of this little triangle, which of course is our delta prime, and then over our adjacent side, which in this case is 15 inches. And we can use this to actually solve for what this delta prime is, and then use that to plug into this formula up here for delta E to get what delta E is. And so that's one thing that we can start off by doing. However, in order to solve for our delta prime, we need to actually have the value of theta. And so there is something else we can do to get that value of theta, and we can shift this deformation diagram downwards. And so basically what I'm doing here by shifting this downwards, I am simply just lowering this entire slanted line by a distance of delta B, and making that left-hand corner of that slanted line just equal to the original position of that horizontal line. And the angle, of course, is still theta. This time, since I just shifted that line down by delta B, each of these points, each of these distances, vertical distances that we had before, we have to add delta B to. So this first one, we have delta C plus delta B. And the second one, we have delta E plus delta B. And then here, we actually know, if you're looking at this second deformation diagram here, we actually know what our delta C is, and we know what our delta B is. Those are the two things that we originally solved for. And we actually also know the adjacent side of this little triangle as well. That's 10 inches. So what we can do now is we can actually use the small angle approximation theorem again to solve for what theta is. So in this case, we have theta is equal to tangent theta. And in this case, our opposite side, let me start writing this out. So theta is equal to tangent theta. In this case, it's going to be our opposite side, so delta C plus delta B over 10 inches. And basically, we're just going to plug in those values that we got before for delta B and delta C. So our delta C is 2.7586 times 10 to the negative 6th times P. And then our delta B is 1.65517 times 10 to the negative 6th times P. And then that's going to be over 10. And basically solving this, we're going to get that our value of theta is equal to 0.44138 times 10 to the negative 6th times P. So still in terms of P there. And basically what we're going to do is we're going to take this value of theta, plug it in there, and solve for what our delta prime value is. And so basically I'm going to go ahead and rearrange that equation down here. So our delta prime is equal to our theta times 15 inches. And then we're just going to plug in the value of theta and get what that is equal to. So we're just going to plug in the values here that we just solved for. So our theta is 0.44138 times 10 to the negative 6th times P. And multiplying that by our value of 15 inches, we basically get that our delta prime is equal to 6.6207 times 10 to the negative 6th times P. And then now, using that formula that we discussed above with the deformation diagram, we basically have our delta E being equal to delta C plus delta prime. And of course we know our value of delta C and delta prime now, so we can find our value of delta E. And that's going to be for our delta C 2.7586 times 10 to the negative 6th times P. And then our delta prime, we just found 6.6207 times 10 to the negative 6th times P. And solving this, we're going to get delta E being equal to 9.3793 times 10 to the negative 6th times P. And so now, going back to the problem statement, they mentioned that our deformation at point E needs to be limited to 0.019 inches. So what we can do is we can actually plug in 0.019 inches for our delta E and then work backwards and solve for P based on that. And basically that's going to look like this. We have 0.019 inches equal to 9.3793 times 10 to the negative 6th times P. And then of course working backwards from there, you're going to get basically that P is equal to 2.0257 kilopounds or kips. And that's the final answer for this problem.